So next we are going to look at power factor testing. Like we said earlier, the power factor testing is used to test the insulation resistance of medium and high voltage assets, electrical assets. Okay, so remember, the insulation resistance test is done by injecting DC voltages into the equipment, but in power factor testing we are injecting alternating current, okay, and then measure the response or responses of the insulation to this changing current direction. So that is what we do in the power factor test. So power factor test, as we said earlier, you can use them to measure dielectric losses in medium and high voltage electrical equipment, and what we are actually looking is the dielectric losses, okay, of the insulation. That is what we are actually looking at as we carry out our test. There are a few things we really need to understand when we are carrying out the power factor test, so that we appreciate precisely what we are looking at. Okay, so in power factor test, what you do is that you are applying potential difference on both sides of the insulation. So which means that you are creating that potential difference on two different let me call them plate-like structure now. Okay, as you can see on your screen, this is a transformer now. This is the primary winding, which is the high voltage side. Then we have the secondary winding, which is the low voltage side. And as we have explained before, there is an insulation between the high voltage winding and the low voltage winding. So that low voltage winding is what will now constitute this dielectric, okay, between the high voltage and the low voltage winding. So if both windings are parallel to each other and separated by an insulation, what we will end up having is a capacitor-like structure, with the high voltage winding forming a plate and the low voltage winding forming the other plate. So when you apply potential difference, okay, that is with the aid of an alternating voltage source, of course the plates will be charged and discharged as the voltage is alternating. Okay, so what you have succeeded in doing is to create a capacitor-like structure around that particular equipment, and that is what we are seeing here. So and we all know that in a pure capacitor, the current is always leading the voltage by 90 degrees. That is when you have pure capacitance, okay, in your system. But we actually do not have an ideal system. That can only happen when the insulation is perfect. But in reality, there is no perfect insulation. So there must be some leakage current, okay? And that leakage current, they are in phase with the applied voltage, as you see here. And that is what is represented by I arrow that goes through the internal resistance of the insulation. Okay, so which means that you have a leakage current that is in line with the line voltage and the capacitive current that is 90 degrees out of phase for a perfect capacitor. So, but since we already have leakage current, the total current will be the vector sum of the leakage current and the capacitive current. So when you look at it now, the vector sum will not be 90 degree. It will not be leading the voltage source or the voltage signal, or the voltage vector, or the leakage current by that 90 degree any longer. So we'll say it will be leading by an angle theta. Okay, so the angle between the capacitive current and the total current at the end of the day is delta. Okay, so cos theta is the ratio between the leakage current and the total current. Okay, so that is the power factor of the equipment. So when you inject that voltage Vs, the what you'll be measuring is the ratio, okay, of the leakage current to the total current as we have discussed, okay, and that is the power factor. So the lesser the power factor, the better for us. We know that the cos 90 is 0, okay. So the lower the power factor, the better is the insulation, because that will mean that the leakage current is very small. If you even consider it with this ratio here, okay, for power factor R over the total current, okay. So if R is small, cos theta will be very very small, okay. So that will mean that that is, if R is small, are we getting it? The power factor will be small. So the tan delta, okay, which is the ratio of the leakage current to the capacitive current, okay, will also give us an idea of the health status of the insulation, okay. That is the dissipation factor. Are we getting it? The amount of losses that can happen or will be incurred when the capacity, that is when the equipment is subjected to such the amount of voltage that you actually subject the equipment to. So it gives us an indication of the losses. So the lower it is, the better for us. That will mean that the losses will be reduced, okay. So the tan delta measurement and the power factor measurement, okay, they come side by side, okay. As you can see, as you are measuring one, you are having an idea of the other. So that is the brief understanding. So know that as you are doing this measurement, what you are actually doing, you are testing the response, okay, of the insulation between the high voltage side and the low voltage side to the injected signal or voltage, and in this case it is alternating current or voltage. So now, what type of equipment can we test with this power factor equipment or arrangement? So like we said earlier, we can test medium voltage and the high voltage equipment, and this includes transformers, okay. So like the example we used, the high voltage side, you inject the high voltage source to that, you connect the high voltage source to the high voltage side, and then you look at the response, okay, from the low voltage side and then the ground, okay, of the equipment. So you can also test circuit breakers, as you can see, okay, when the contacts are open, that is between poles. Are we getting it? When the contacts are open, testing the insulation that is separating the contacts, okay, on a single pole. And you can also test the insulation between the different phases or the different poles. Are we getting it? Okay, and also the each pole to ground, to test the insulation of each pole to ground. So you can use it on circuit breaker. You can even use it on all of these lightning arrestor, okay, to get the insulation of the line to ground, okay, whether it is still as fit. Then this connector switches like the circuit breaker between poles, between pole to ground, and okay, basically those are what you can actually test on the isolator. Okay, then on generators too, you can use them, but in this case you can, like we did in the insulation resistance test, you can test between winding and ground, or you can disconnect the start point and test between each winding. Okay, that is the U to V, V to W, and W to U. Okay, that is between the phases, and also between phase to ground. Okay, but a general test between the winding and ground will give you an idea as to the insulation level of the insulators that are used to separate the windings from ground in the alternator. But that will not give you the insulation, uh, the head of the insulation that is separating each of the windings. So for you to know that, you have to disconnect the start point, okay, and then carry out the power factor test between the phases. So you can also use with the motors. On the motor, remember we have windings on just the stator. Okay, so we can test the stator to ground, and as we did on the motor, we can disconnect the start point or disconnect the data connections and then test between each of the windings. Remember, these are high, medium voltage and high voltage equipment. We can also test cables. Okay, we can, as you see on the screen now, we can test a particular cable to ground. Maybe we are using the, if it is armored cable, the armoring. Okay, we can test between the armoring and the conductor itself. That will give us the insulation, the nature of the insulation, okay, between the armoring and the conductor. But in this type of cable now, we can use this shield, okay, and the conductor, and that will give us the response of this insulation. So with that, we'll be able to know if this insulation is perfect or not. But if we have more than one core cable, okay, maybe we are having a 3-core cable, we can test between each of the conductors, okay, between red and blue, between red and yellow, and between yellow and blue. So that will give us the insulation between those, the nature of the insulation between those conductors. So we can actually deploy the power factor test on all of these assets, electrical assets. So let us now look at the test procedures. The test procedures, okay. So we can use the power factor meter, okay, or test instrument, or the turn data test instrument, okay, to carry out the test. So now the first thing that we need to do, remember the test is not a live test, so we need to take out the instrument from service. That is, we need to de-energize, okay, and make the equipment safe for the test. Okay, that means after isolation, we need to test if there is voltage, and then at the, that is discharge whatever charges that may be there, we discharge the equipment, since we are dealing with high voltage, medium voltage and high voltage equipment. Okay, so we'll make it safe for our test after isolation. So we'll now inject with this equipment that you are seeing here. We'll now inject an AC voltage, okay, that is at most at the nominal rating level of the equipment. Are we getting it? Or below the nominal rating of the equipment. So what we are saying here is that if the equipment is an 11 kV equipment, we can inject 11 kV or below alternating voltage signals. Okay, so that is what we will inject. And then at the same time, as we are injecting, we measure the dielectric losses and the power factor, okay, whether to ground or, as we'll see later, in the various mode of tests, okay. So once we take the measurement, we need to correct the measurement to standard conditions. Some instruments, they are designed to correct to 20 degrees Celsius, okay. So we need to correct it to that. So if you use such instrument, they will do it automatically for you, or else you have to manually do the calculations. So the test results that you get at the end of the day, of course, this highlights the importance of trending your results. Are we getting it? You can compare your test results with what you had previously or industry accepted values. Okay, so once you compare it, then you will know if the insulation is actually deteriorating. But remember, whether you are looking at the power factor or you are looking at the dissipation factor, that is tan data, the lower the value, the better for all of us, because that will mean that the insulation is close to perfect. Okay, the leakage current is small in that particular case. So this is a typical test set of for power factor. Okay, so here we have the high voltage output lead, which is this. This is what actually injects the high voltage into the equipment that you would want to test the insulation of its insulators. Okay, then we have the ground lead. Okay, that ground lead is basically for grounding the equipment. Okay, connecting it to the ground of the equipment that you want to test. And then remember, the equipment will also have its own ground, so that ground will be secured, and then the ground of the equipment connected to that particular ground. Then we have the red or the blue lead, okay, which is used to guide the current, okay, that is not flowing through it's actually used to direct the flow of the current, okay, either into the ammeter of the instrument or out of the ammeter of the instrument. Are we getting it? Depends on the test mode that you actually want to adopt, as we'll see later. Okay, so like here now is for the ungrounded specimen tests. Okay, so you use it to actually, since it's ungrounded, use to direct the current that will be flowing to ground. Okay, from the ground, I mean to say, out of the measurement instrument. Are we getting it? So we'll see all of this later. So remember that we said when you are doing the power factor test, what you are actually creating inadvertently is a capacitor-like structure. Okay, if you are using the transformer that we use as an example, you will see that the high voltage side will form a plate of the capacitor, and the high voltage side, the low voltage side will form the other plate, while the insulation between them become the dielectric. Okay, so as you inject your alternative voltage, as we said, those plates will be charged, and there is, since it is alternative, there is bound to be flow of current. Okay, so now if you look at it, you will see that the three different type of test mode. One, we have the ungrounded specimen test. Okay, when we say ungrounded specimen test, that is the current that is flowing from the ground terminal of your equipment is not included in your measurement. Then we have the grounded specimen test. Okay, and then we have the grounded specimen test in the guard mode. Okay, so the difference is that in the grounded specimen test, as you can see, the current, leakage current flowing, that is the current flowing from ground, is also directed into the instrument measurement apparatus. Okay, so you capture the one that is flowing through the ground and also the one that is flowing through your equipment. So that is the grounded specimen test. Then the one with guard measures only the one that is the current that is flowing from the ground of the equipment, as you can see here also. Okay, so when you look at it, this, if you are not too familiar with this, it may be a kind of confusing. Remember, we said if you are connecting between the high voltage and the low voltage, you are like creating a capacitor. Okay, so that is what you have here. This is the high voltage side, which is where you inject the high voltage from the equipment. This is the high voltage terminal. We'll see it later. Okay, and this is the low voltage terminal. So the insulation between them, okay, is what will now form the dielectric of this capacitor. Okay, so this capacitor is what we now refer to as the CHL, that is the capacitance of the high to low side of your equipment. So here is the high voltage side winding and this is the low voltage winding terminal. It will become clearer later as we look at it. Then this one to ground, okay, remember there is an insulation also between the winding and ground, between the high voltage winding and ground, as we explained in our earlier section, between the high voltage winding and ground and between the low voltage winding and the ground. So when you look at it, that is what will now form this capacitance. So that is capacitance of low to ground and the high winding to ground. So this gives us the insulation between the high to ground and the insulation between the low to ground. Okay, so whatever that is current that is flowing through here is one that will flow through the high to low. The one that will come through here, okay, you see that it will be the high to ground. So if you look at the different mode of tests that we have, so if you select, or if you are doing the ungrounded specimen test, as you see on the left side of your screen, okay, what you are actually doing, because you can see the connection of the ammeter, so whatever that is flowing through this line from the high to low is what you are going to measure. Okay, that will give us an idea of the power factor, okay, of the insulation. That is an idea of the insulation, that is the dielectric strength, so to say, of the insulation between the high voltage and the low voltage side. Then if you look at the second test mode, which is in the middle, okay, the grounded specimen test, you will see that in addition to the current that is flowing from the high to low, okay, you also have the one that is flowing from ground to your ammeter, to your test equipment. Okay, so you have the addition of this and this. Then if you look at this, you see that the ammeter you are bypassing, that is the grounded specimen test with the guard, okay, the guarded grounded specimen test. You see that you are bypassing this high to low, okay, so which means that you are measuring only what is flowing through the ground. Are we getting it? So basically these two, if you subtract them, you are supposed to have something close to this. So it's basically to confirm what you did in the ungrounded specimen tests. Okay, so let us see how we do the connection. So remember that we are taking the high voltage windings, the three phases, as one winding, okay, which means that we have to short the three of them. The 3 terminals of the high voltage side of the transformer, then the 4 terminals of the low voltage side of the transformer. Remember, since it is starred, we have a neutral point. So we short the 4 terminal, we short these 3 terminal. Okay. So now this is the diagrammatic representation, okay, of what is inside this transformer that are connected to these terminals through these bushings. So when you look at all of this, you'll see that these are the 3 terminals, okay, and then these are the 4 terminals. So the high voltage side of your instrument, the high voltage cable or test lead, is connected to the high voltage side, okay. Then the low voltage lead is connected to the low voltage side of the test, which is this part of your transformer. And then the ground lead is connected to the ground of your equipment, okay. So with the appropriate selection, whether you are doing ground specimen test, ungrounded specimen test, or ground specimen test with guard, okay, you run your respective tests and measure your test results, okay. So similar thing is happening here. You see all the terminals of the high voltage bushings, okay, they are looped together, as you can see here, and then the high voltage lead is connected to them, and then all the low voltage terminals are connected together, and then the low voltage lead is also connected to them. So what we have is somewhat like this, okay, as we saw earlier. So the frame of your transformer is now your guard, is now your ground terminal for your equipment. So this is the data 4000 power factor test set. So the connection is as simple as indicated in this your diagram. So this is the high voltage source, okay, and this is the high voltage cable that is sent to your high voltage terminal of your transformer. Remember, this connection is the same as we've had before, and then this is sent to the low voltage terminal, and then the ground terminal, which is this green lead, is connected to your equipment ground. So with this test, you can measure the power factor and this is the dissipation factor to determine the amount of losses that you could incur in your transformer, the insulation of the transformer. So here are some, let me say, a rule of thumb or some idea about what should be acceptable in your measurement, okay. So on the left of this table, we have the ratings of the equipment, okay. So if it is high voltage oil field, for new equipment, the dissipation factor should be, that is the tan delta, okay, value should be very, very low. You see, this is 0.0005. Are we getting it? Remember, it is a ratio, so there is no value. Then if it is used equipment, 0.05, okay. Then if you have something close to 0.01, which is higher than what we have here, then it becomes questionable, okay. For the low voltage oil, low voltage equipment oil, 0.001 for new equipment. See, it is somewhat high, okay, compared to the high voltage oil used for high voltage equipment. Then 0.01 for used equipment. Then if it is 0.03, as high as 0.03, then it becomes questionable, okay, which means that you need to do what you have to do to improve the insulation. Anything above this, you need to do what you have to do to improve the insulation. So for equipment that are less than 19 kilovolts, these are for new equipment, this is what is acceptable, 0.01 kilovolts. Then if it is used equipment, 0.03, that is equipment that has been in service for some time, 0.03. Then if it is as high as 0.09, it becomes questionable. Then anything above that, you need to do something to bring it down back. So between 20 and 80 kilovolts, 0.007, okay, for new equipment, 0.015, okay, for used equipment, and anything above, that is from 0.03 and above, becomes questionable. And as it is increasing, of course, it means that you need to do something to bring the equipment back into service. So 90 to 200 kV, this is what we have. Okay, this one we are already going to the extra high voltage region. Okay, so these are the acceptable dissipation factor, and whenever it is above this, we need to do something. Okay, which means that the insulation of the equipment is already deteriorating. Are we getting it? There are some considerable amount of losses already occurring in that insulation, that if left unattended to, may result to failure of the insulation and eventually the equipment. So that we do not actually want. Okay,